of session of the Proof Complexity Workshop. Really happy about the speakers overall and this session also. We have Neil Thapen and Sam Buss, who will be talking about the connection between proofs in restricted systems of bounded arithmetic and how they're closely connected to TFNP search classes. This connection started a while ago, a long time ago. Actually, Sam Buss was the first person to really make it very explicit, these systems of bounded arithmetic and the strong connections between proofs in those systems and TFNP search classes. So it's a real, and Neil Thapen, our first speaker, has also done some real foundational work in the area. So I'm really happy to have them here to tell us about, survey the area, but also tell us about new work. And then another part of that we'll continue the beginning of the next session. Robert Robert will talk, this is tomorrow, Robert Robert will continue to talk about TFNP and some exciting recent developments from the point of view of propositional proof systems. So we'll start with Neil. Take it away.
Okay, thank you very much, Tony, and thanks very much for inviting me to talk here. I'm very happy to tell people about this. So, wait. Okay. Yeah, so first of all, here are just some references. So yeah, so this goes back maybe 25 years to this paper of Buss and Krajicek at the top that talks about PLS, which I'll come to. And what I'm going to say is mostly some sort of survey of some work on this, and it's summarized in the last paper by myself and Leszek Kołodziejczyk. So I'll give some introduction to TFNP, as there's going to be a couple more talks on it, and then talk about logical background, and then describe and give some pictures of some TFNP classes coming from this kind of logical question. So just as an introduction, often in complexity theory, we're talking about decision problems with 0-1 answers. So given a graph, you want to decide, for example, whether it has a Hamiltonian path, and we have classes P and NP and P space and so on that contain this kind of question. But we're talking of search problems where the answers got even more complicated. We want to find something and output it. And in the example here of Hamiltonian path, it's possible that there isn't one, and we have to deal with this. But that's not what we're going to do in TFNP. So here we're interested in search problems. Can you see the pointer here? Yes. Where the thing being searched for always exists. And also, to keep things tidy, it's recognizable in polynomial time, and it's not too big. This is the thing being searched for. So these are also all the properties of the witness to an NP property, as we'll see on the next slide. So the class of the problems is called total functional NP, or TFNP. Oh, and I should say, please interrupt with questions at any point. So here are two examples of problems, and I'm going to write the problems in yellow. So this one is called Pigeon, and the input looks like this. It's a number n in binary. So the kind of interval described by the number is exponential size in the length of the number, and it's a circuit. But you kind of gloss over the details of this a bit, and you think of the circuit as just determining a function, in this case from n+1 to n, and then you're interested in some property of a function. And so we know by the pigeonhole principle that any such function must have a collision, and the search problem is to find this collision. And I'll talk later about weak pigeon, which is something similar, except it's a function from 2n to n. And here's another example that I'll come back to a little bit, RAMSEY, based on the finite RAMSEY theorem. So again, the input describes a large graph, an exponential size graph. We know any such graph must have a clique or anti-clique of a certain size. And so here's the search problem of finding that anti-clique. All right, or clique. So just to give a formal definition, we have a p-time relation R, and the problem is to find some y satisfying this given x, and the y has to be less than a certain size, and it has to be total. So this sentence, that for all x there is some y satisfying it, has to be true. And we'll just say R as the name for this kind of problem and ignore the rest of the structure when naming it. And just to say a bit more about the sentence here, this is a sentence with variables ranging over binary strings, which we will also treat as numbers. And as I said, normally the input is some kind of compactly described large object, and we want to find maybe some substructure of this object. And so far I've talked about the structure being described by circuits, but often it'll be described by an oracle. And that's what will happen when we're proving separations. So we can compare two problems. If we have problems P and Q, we say P is reducible to Q if we can solve P with the help of one called a Q. And formally that looks like this. We have these helper functions f and g. So we want to solve P at x. So this says that we get a instance fx of Q. And if we can get a solution to Q, then we can, again in polynomial time, make that into a solution for P. So we solve Q here to solve P here. And it's equivalent if you have this reduction in both directions. So here are some classes. So a basic one is the problem solvable in polynomial time. So any polynomial time function can be seen as a NP search problem just to find its output. And there are other well-known classes, PPAD, PLS, this one for the pigeonhole principle. And these are usually defined as all problems in TFNP that you can reduce to a specified problem. And so here we have the class PPP defined in terms of the problem pigeon. And I apologize, I'm not going to be very good at distinguishing between the classes and the defining problems. So sometimes I'm going to use the name of a problem for the name of the class, and maybe vice versa. So these sort of live in between P and NP. And if P equals NP, then they all collapse down to the bottom level because we can just search for a solution in P. And I'm going to talk about the structure of the classes and have some pictures of it. And the idea is that we want to understand the different ways in which these problems can be hard or easy. So here is the first picture. So here are some fairly well-known problems. I'm not going to talk much about these ones here on the left, although you can sort of fit them in this structure. I think Robert will talk about them. I'll talk about PLS. And here we have some combinatorial problems. So this is the weak pigeonhole principle, where you have to find a collision on a function from 2n down to n. So this is, on the face of it, much easier than this one. This is some kind of ordering principle, where you have to find a least element in a binary relation that's an ordering. And this is the RAMSEY principle again. And I'll come back to PLS. And yeah, so these arrows indicate containment of classes, or if I'm, well, really here, this is a search problem, but I kind of mean the class of things reducible to these problems. And they're related like this. So here's some logical background in the 20th century theories of arithmetic. So by a theory, I'm just going to mean a set of sentences, and they'll be saying something about the natural numbers that's maybe true and is maybe false. And so standard example is PA, pure arithmetic. It has some axioms for ordered rings, and then it has induction. And I just want to mention this kind of old picture of breaking down pure arithmetic into induction for increasingly strong formulas. Here's pure arithmetic in the middle, and then if you want, you can consider even stronger systems with some kind of second order reasoning. And there's a system developed for measuring the strength of these theories. The theories can be kind of different kinds, but they can all talk about computation and recursive functions. And a useful kind of measure of the strength of the theory is the set of functions that they prove are recursive. So each one along here can prove that some set of recursive functions are total, and the set gets bigger as you go from left to right. And there are some nice ways to measure the increase in strength. there are these ordinals. So in this case, there's this kind of towers of omegas measuring the subtheories of PA, or there are fast-growing functions. So for example, the Ackermann function is total here, but isn't total here. And the functions you can define get faster and faster as you go to the right. So this is a picture we'd kind of like to have in bounded arithmetic, which I'll come to. But these kind of things, these kind of ways of separating them aren't available. In particular here, sort of every theory is going to prove the consistency of the theory on the left. So we know they're getting stronger, and that doesn't work in bounded arithmetic. And fast-growing functions won't work in bounded arithmetic because all functions are polynomial. So this slide is really for my motivation for this work, is to try and find some different way of looking at the strength of induction in a more complexity theoretic setting. So I guess that's already approach to this on the next slide. So rather than talking about recursive functions, we're going to talk about TFNP problems. And given really any theory T, we'll define TFNP T to be the set of TFNP problems that the theory proves is total. So by proves, well, this is just normal first order logic, and we have to have some way of expressing that R is total. And so we're going to be working in a language that has a name for every polynomial time relation and function. So here are some examples of these. So here's a relation, here's a function, here's a relation. And in this language, we can express R is total, and it's just the sentence we saw before. For all x, there is some solution to R. And as before, the variables are formally binary strings, but we treat them as though they were numbers. So we will take as a base theory, but actually all theories are going to extend, this one, where we take every true universal sentence, where universal means it's a universal quantifier followed by something in no quantifiers. And the things we have in no quantifiers in a language are just sort of Boolean combinations of polynomial time formulas. So this is polynomial time. So the point of taking this particular theory is that the sort of basic properties we want to have all have this form. So for example, the condition that Q is reducible to P is exactly this form. It's a universally quantified polynomial time sentence. So we get from that the first line of the proposition that if we have a theory containing this, then the class of TFNP problems is closed under reductions. And this is something that any natural class of TFNP problems should have. So this avoids some problems having this. And also it so happens that also these algebraic axioms say about the commutativity of ordering are also contained in this theory, since they're universal. And also this will remove questions about which name you use to define some polynomial time function, because if two machines define the same function, then that's provable in base. And for the kind of questions we're interested in about TFNP, the theories don't really get any stronger by adding this. So here are some simple examples of what we can get. If we just take our base theory and we ask what TFNP problems are total in this, then really the only things that you can prove exist in base are things that are given by polynomial time functions. So if you can prove something is total, then you can probably construct it using polynomial time functions, and in fact you get FP, and this is basically Herbrand's theorem. If another natural thing to do is to take our base theory and add that some problem is total, and then in the case, say, of PLS, that the set of things you'll get here is PLS again. But this isn't always going to be true. You'll get the class itself, and you'll get things that are that you can get by finitely many calls to the class, and you might get some other things as well. But for a kind of robust theory, you'll get back the same thing. An interesting case is if you take some very strong theory, such as Peano arithmetic or set theory. So this still makes sense, as we just have some property of numbers, and these are quite good at talking about numbers. But here, I'm not quite sure what's going to happen. You get a strong set of sentences of problems. If you don't have base, you can't get everything, because by Gödel's theorem. because consistency can be written like this. So PA is consistent. So this search problem is total, but PA doesn't prove it's consistent. Itself is consistent, so it won't prove this is total. If you add base, I guess I'm not quite sure what you'll get, and there are some papers discussing this kind of question. And lastly, if you just put in all true sentences, which is a valid theory, then you'll certainly get all of TFNP. So I'm not insisting this set of sentences is particularly recursive or uniform or anything like this. I'm allowing any set of sentences here. Any questions so far?
Just Scheiben David gave a talk last year in 2020 about PA1.
Mm-hmm.
This base and PA, is this PA1? He proved that PA1 can, with PA1 one can, if P is NP, then it must be in PA1. So it's, I think.
Okay, I don't
know PA1 maybe.
No, I don't think it's, well, it's
okay,
not a bit of notation.
I think it's the same, yeah.
To me. So, I mean, it's a bit far from beyond arithmetic since it's based on complexity rather than the algebra exaf, but it could be. I don't know.
Okay.
Okay, so I'll go on to talk about bounded arithmetic and some classes in TFNP that gets you. So bounded arithmetic is like a resource bounded version of Peano arithmetic, which means that in Peano arithmetic we can talk about unbounded quantifiers, and we can do very long computations. In bounded arithmetic, the quantification is limited, and this corresponds to resource bounded computation. So I'm giving a rather non-standard definition of it, but one which kind of avoids all the technicalities. So I'm going to say, so this would be called basically TK2 in SAM setting. And we have a base theory, which is just these universal properties of polynomial time sentences. And then we just have induction for every sigma pk formula. So induction means just the normal thing. And sigma pk also means, I guess, the normal thing. So it's level k in the polynomial hierarchy. So sigma p1 is np, and then we put more and more bounded quantifiers. So sigma 1 induction is just base plus induction for np formulas. So one usually has to be a bit careful in the properties are kind of semantic and the formula has to be syntactic. So a formula should really specify which particular machine you're talking about, which has your property. But in this case, we have this theory base available, which just says that if two machines calculate the same polynomial time set, then the theory proves they're the same. So in the presence of this, we can just talk about these properties and we don't have to really be careful specifying a machine. So we're just talking about induction for NP formulas or induction for NP to the NP and so on. So this kind of theory gives a natural way to reason with and about concepts from complexity theory. And so if you want to ask questions, say, about provability of P equals NP and things like this, it's a natural place to ask them. And there's some recent work about these questions. But not really doing that. We're going to use sort of witnessing properties. So one of these is to do with that a bounded arithmetic proof can be translated into a small uniform constant depth Frege proofs. And this is something we're using silently, since some of the theorems I state will use that. And we also have the following, which is sort of the witnessing theorem. So it says the kth level of this theory proves that every P to the sigma pk machine has a computation on every input. So in particular, say on level 1, P to the NP machines are definable. And there's a converse. So the converse isn't quite, so the converse is something like the statement that every machine has a computation implies the theory This isn't completely true, but it's conservative for a big class of sentences. So in particular, if we're just interested in which TFNP problems are provably total, that's a pi2 formula, and that's going to be the same between these two theories. So if we take this, if we look at the TFNP problems provably total here, it's going to be the same as the TFNP problems provably total here. So that's what I mean by its equivalent. So here is another example of a TFNP problem. It's one I had in my picture. So strictly speaking, this problem is sinc of DAG, and it's about you're given a directed acyclic graph, and you want to find a sinc. And you have to be a bit careful to specify what you mean by acyclic in this case for this to work. And yeah, so this problem defines the class PLS, and I'm just going to call this problem PLS to have one less definition. And this class gets used a lot and is equivalent to lots of things, in particular finding local minimums in reasonable situations. And so the kind of oldest connection of bound arithmetic and TFNP is this one of Buss and Krycek in '94, that if you take this theory, which is, well, Buss's T12, or its induction for NP formulas, then the TFNP problems it proves total are exactly those in the class PLS. So, yes, so 10 years later, we were able to extend that a bit higher up these theories. So CPLS, colored PLS, I won't give the full definition, but it's something like PLS, but has some extra structure. So rather than just having a DAG, you have a DAG where each node is labeled with a set of colors, and there's some condition on the relation between the colors of a node and the colors of its successor, well, its neighbor in the graph. And you have to search for a sinc, or you have to search for somewhere where the colors don't quite match up. And we can show that if you now go one level up the hierarchy, so this is induction for the NP to the NP formulas, then you get this class CPLS. And the proof of this is through a translation of proofs here to resolution proofs. And really this CPLS is kind of a combinatorial version of the reflection principle for resolution. And so this is somehow the strongest thing that's kind of a reasonably nice combinatorial statement that has a short resolution proof. So it's quite useful for proving lower bounds of systems around resolution. And then we are able to go further and get some more principles. I'll have a picture in a moment. So again, I haven't given the full definition here, but this is a statement about you have a sequence of games, and you have some kind of polynomial time machinery that tells you that player B wins the first game. And you also have machinery that is able to make a winning strategy for player B in game I into a winning strategy in game I+1, and there's exponentially many games. So kind of inductively, if you could do some big induction where you can compute some big strategy, you could find a winning strategy for B in the last game. So winning moves must exist for any move of A. And here is, well, this is a version of the principle where the problem is to find these winning moves. So yeah, so we have the theorem that if you have the kth level in the bounded arithmetic hierarchy, then the TFNP problems that are defined by this is the kth one of these game principles. And let me just mention some equivalent problems. So one of them is a generalization of PLS. So in PLS, well, one version of it was finding a local minimum on a constant degree graph. So here is a version where, say, for k equals 2, rather than just a minimum, you'd have to find a kind of minimum of maximums. And for k equals 3, you'd have to find a minimum of maximums and minimums compared to the neighbors and so on. Here's another equivalent statement. So it's a kind of Nash equilibrium question. So it's about a succinctly given game with k turns and 2 players. And so a player can have a strategy and then to score something, and the other player has some strategy. And usually the Nash equilibrium is some kind of local thing where neither player can improve their strategy. And this is a kind of version of this where the players are only allowed to make polynomial time revisions to their strategies. So it's not that they can't improve it, but that there's no improvement they can find in polynomial time. So for a k-turn game, this is equivalent to these principles again. So here's the picture of what these things look like. So I've deleted some of the lines down here for clarity. And so we have these extra things in the middle. So PLS, which is the same as GI1, CPLS, GI2, and all these other ones. And we're beginning to have this kind of backbone going up the middle, I want to call it. And because we've studied what you can prove in bounded arithmetic, we can draw some lines here. So we know that the RAMSEY theorem is provable in GI3. And we know that the weak pigeonhole principle, this ordering principle, are provable here. So we begin to get some kind of handle on where these things sit. And now I can mention again what the main open problem is in this area as I see it. And it's to actually separate the search problems along the spine here. So my motivation of this comes from logic. So I see it as the question is to show that if you have induction for formulas with k+1 quantifiers, then it's stronger than induction for formulas with k quantifiers. So this should be true. Certainly it should be true with respect to some oracle, but we're not able to prove it beyond this level. As far as we know, everything could collapse to here. And this is essentially the same as questions about separating depth k from depth k+1 in constant depth Frege. And then we can go a little bit higher up. So we also have second order bounded arithmetic theories. And these quantify not just over numbers, but over kind of sets of numbers or over functions or effectively over oracles, exponentially large things. So V12 is kind of a straight induction existentially quantifying over these objects. U12 is a more limited induction. And these are defined by Sam. And there are these connections between p-space and exp-time. So U12 proves p-space machines have computations. V12 proves exp-time machines have computations. And again, there's a kind of converse for most sentences, and certainly for the sentences you're interested in. So for us, the statement that p-space machines have computations proves this, well, proves the consequence of this, and the same for exp-time and this. And these theories are uniform versions of Frege and extended Frege. I guess Sam is going to talk more about this. And in particular, this U12 is like Frege. It can do counting, and it's good at proving combinatorial statements. So basically, anything you write down, often even if it looks rather hard to prove, you can find a U12 proof of it. So yeah. And so we can describe some kind of combinatorial principles capturing these. So again, I haven't written out all the details, but one is the local improvement principle. So this is going to be for V12, and the input is a directly acyclic graph, and it's large. And so this labeling I'm discussing is in principle some exponentially large thing. But the principle just talks about local changes to it. So there's nothing kind of exponential in the principle itself. So it says that given a labeling of some part of this graph with some good property, we can relabel it to get an even better property with a better score. And then if we had exponential time and space, we could find some very good score, but the principle just says some labeling with a good score exists. And there's a restriction of this, where rather than a general DAG, you just have a line, and the scores are limited or they're rather small. And we get these characterizations. So there was an early version of this that I had with Leszek Kołodziejczyk and Fong Nguyen, and this is improved by Sam and Arnold Beckman. that this local improvement principle captures U12, and this restricted one captures V12. So if we put these on the picture, we get this. So again, in the middle, we have these first order bounded arithmetic. And then at the top, there are these principles based on the second order systems. And now, because we know that U12 is good at proving lots of things, in particular things based on counting, pretty much any natural TFNP problem is going to be reducible to this principle. We don't have many explicit reductions, but we know something exists just from the proof theory side. And let me mention that there was a recent paper of Papadimitriou and Goldberg talking about some similar theory, some strong theory that seems to formalize arguments, a lot of arguments showing TFNP problems are total, and it lives somewhere up here. I'm not sure where it lives. And I've just drawn here as well this note that because of Buss's theorem and this connection between the theories and the types of computation, we've got another way of looking at these principles. So this one, say, is actually the set of TFNP problems that are provably total under this assumption, which is my shorthand for the statement saying that every X time machine has a computation. And this one says that every p-space machine has a computation. And this one says that every machine, well, in the polynomial hierarchy at different levels, has a computation. So you can kind of see these as some sort of shadow in between P and NP of all these stronger principles. And this can be a little bit confusing at times because, say, at this level, you're already, no, further down at this level, you're already talking about P to the NP machines. So given any TFNP problem, you can solve it with a P to the NP machine just by searching for solutions. But yeah, so if you can show the problem exists, then you can find it with a P to the NP machine. But if you don't know that a solution exists, then giving yourself the assumption that P to the NP machines have computations doesn't necessarily help you find it. Find a solution. I mean, if it did, this would all collapse. Yes, so now I'm going to go on about approximate counting. So are there any questions about this?
I'm a bit confused about PLS versus CPLS. Which one corresponds to resolution? Is it PLS or CPLS?
CPLS, well, so the most accurate thing would be to say that CPLS corresponds to res log. So it's set up as reflection for resolution, but it's kind of in a setting where you can't tell the difference between resolution and res log. And then PLS is going to be like small width resolution. Okay. Any other questions? Okay. So yeah, so this is a picture of TFNP, and for a lot of principles, you can maybe think about where they live based on provability here. This doesn't work so well. At least focusing on induction doesn't tell you so much about these things here because well, they're not provable using induction. But you could set up a different approach that deals with those, and I think that's what Robert will do. Okay, approximate counting. So these three problems I picked out: the weak pigeonhole principle, this ordering principle, and the RAMSEY principle. Well, the search problem. We can prove all these search problems are total using arguments based on approximate counting. So for the weak pigeonhole principle, this is kind of obvious because if we can do some counting, we know that 2n is bigger than n. The ordering principle is a bit more complicated. I'll skip it. And for the RAMSEY principle, we have this very kind of well-known proof, which usually uses counting, but I just want to say approximate counting is enough. So we're given some graph G of size n, and we want to find a clique or anti-clique. So the procedure is we choose some node, it can be the first node, and then either it has an edge to, well, you might say half the other nodes, or it has, well, either there's a set of half the nodes it has an edge to, or a set of half the nodes it doesn't have an edge to, and you take whichever one's bigger, and then you take one of those nodes, and either this has an edge to half the rest or not to half the rest, and you keep on doing this. And after log n steps, you have enough to find a clique or an anti-clique. And you don't need precisely half to do this. If you do it with a half minus epsilon, then things will work out in the end. It looks like you maybe lose one or two from the size of your clique, but you can kind of fix that. And looked at this way, you can see some reasonable error here. The argument's still going to go through. So this is what and this kind of thing is what I mean by approximate counting, where you can count things, a little bit of error is okay, and using some kind of induction on this counting, you prove something. So some questions about this are, is there a formal theory capturing this kind of counting? If we did have such a formal theory, then we can ask the next question, which is, lots of our examples seem to be provable in approximate counting. You can prove a lot with approximate counting. Can you prove kind of everything, at least that lives on the bounded arithmetic side, with approximate counting? And then the last question is, well, it's the old question again. So I had this old question about collapsing down to a level of CPLS, and I'm just writing it here to compare it to this question about approximate counting. So here are some answers. So there is a formal theory, which I'm going to give next. And no, it's not the case that everything is provable in approximate counting, which I'll show. And then, yes, this is just the main open problem. So this no answer here is kind of almost, but not quite, a partial answer to question 3, since the approximate counting theorem is going to be kind of cousin to this theory. So this is the theory of approximate counting developed by Emilia Jarbeck. So we'll call it APC2, and we take induction for this kind of formula. And we had this theorem that this is the right theory for formalizing P to the NP functions. In particular, it proves their total. And so in the presence of this, we also have an axiom about P to the NP functions, which is this retraction weak pigeonhole principle. And it says, this should be a comma, it says, you can't have a surjection from n to 2n with an inverse. The important thing is really the surjection part. So if you take this theory, then through all kinds of machinery about sort of de-randomization and sampling, you can you have a simple way to write down an expression for the approximate size of a set, and you can do induction on this, and so you can formalize proofs using it, such as the one I gave of the RAMSEY theorem. So that goes through in this theory. Yeah, so the theorem here is the answer to this question. So we show that although approximate counting is strong, it doesn't give you everything. So we're able to get some separation here, and this actually turns out to be it's a separation between search problem classes, as we'll see in a moment. So yeah, let me skip forward to my picture at the end, because I just want to show here. So I'm going to define a class of search problems. I'm going to sort of generalize this question. We have these things provable in approximate counting. You could define a general notion of NP search problems that are provable in approximate counting, and I'll show a separation between these two things. So yes, so to set this up, we will define a sigma P2 search problem to be like a TFNP problem, but in a TFNP problem, the basic property is P time that we're trying to find a solution to. And here we're allowed it to be co-NP rather than P time. So there's a universal quantifier hidden in here, which means that if somebody tells you Y is a solution, It might not be. There might be a counterexample which you can maybe find. And now we have a definition of a TFNP problem, now normal TFNP problem, being reducible to a sigma 2 search problem in a certain way using PLS. So I guess I'm running out of time a bit, but the idea is we're given X, we want to find a Y, and so we go through finding a solution. We're given some solution to this sigma 2 problem, and it may or may not be a correct solution, but using it and using a kind of machinery to solve a PLS problem, we find some Y. And then either Y is the thing we wanted, or it's a counterexample showing that this thing is false. So this is a kind of reduction of normal problems to sigma 2 problems. And now we can define a class of sigma 2 search problems, which are going to be all the instances of this retraction weak pigeonhole principle. And we can define a class approximate of the TFNP problems, which are reducible in this sense. And then we can show this gives you exactly the things that are in APC 2. And so to show that APC 2 doesn't prove something, we've sort of translated it in this more computational setting, and we'll answer that by constructing an oracle relative to which this there's no reduction of this kind. So this is what we want to prove. And the idea is to use a random restriction and a switching limit. So
Sorry, Neil, I just wanted to mention you have about 3 minutes left.
Okay, so this is the last slide pretty much. So we'll construct a random oracle, and we do it kind of in a way that doesn't give a solution to CPLS, but then we use our kind of switching lemma to actually show that lots and lots of NP queries, which are something like a KDNF, get their answers fixed for a suitable notion of fixed. And this means we've fixed the output for lots and lots of P to the NP machines, which in particular means we're able to kind of fix a witness to our weak pigeonhole principle. So we've done this without giving a witness to CPLS. So this gives the separation we want. So yeah, so I can go back to the slide showing this picture now of some subclasses of TFNP. So that we can get from these bound arithmetic theories. Okay, that's it.
Excellent. Great talk. Any questions?